solutions to the vectors problems.
No, but we can turn in vectors today, and we can turn in 2D particles. No, it's part of 2D. Oh. No, it's a 2D one.
Oh.
Oh, wait. It's the third. It was the third homework, I think, that I did. It was the one that was 11 questions, and it was the one that was gone the day that it was due. It was due a week ago from Tuesday.
Oh, right. That was supposed to be along a line, not the new one. That's supposed to be like a review. Okay. Who wants to take their assignments back and just give it to me Tuesday? Just don't turn anything in today. There's confusion. The one from Tuesday, well, I don't have those with me, but yeah, same thing with those. Tuesday, yeah. Yeah, turn. Yes, this is, and actually anytime it says even or odd, that's review. You're supposed to do the same problems again. Okay, but yeah, sorry about that. I need to be more clear on that one. Okay, yes, right, exactly. Okay, anybody have any homework questions? You do. But I'll get to that stuff today. Yes? Sure, do you have it with you? Great. On particle kinematics along a line? Is it the object moves according to the acceleration function? Okay. Hey, look at that. I never knew I could do that before. Okay, so the acceleration function is 2 times the cosine of 4t. And we're trying to figure out when does the object change directions. Can we use the constant acceleration equations for this? You know, those 6, well, those, along a line, it's 3 equations. The PF equals P sub 0 plus blah, 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 all those equations. No, because that's not a constant, you know, right. So for this one, we're going to use the fact that the velocity is the integral of the acceleration and if we need it, we'll use the fact that position is the integral of the velocity. Okay, so velocity is the integral of 2 times the cosine of 4t dt. How do we solve this integral? Yeah, u substitution. So u is equal to 4t du dt is 4. So dt is du over 4. Is that the notation you guys are used to? And then, so the velocity function is the integral of 2 over 4 times the cosine of u du, which is 1/2 sine of u plus c, which is 1/2 sine of 4t plus c. When time is equal to 0, the velocity is 1. And so 1/2 times the sine of, 4 times 0 is 0, plus c, that's the velocity, which at that instant in time has to be equal to 1. Sine of 0 is 0, so c is equal to 1. And so the velocity function is 1/2 times the sine of 4t plus 1. And then there's going to be a problem here, isn't there? At what time between 0 and 0.75 does the object change direction? How are we going to specify when it changes directions? Velocity is equal to 0. So we want to find a time where velocity is equal to 0. So set 0 equal to 1/2 sine of 4t plus 1. So let's see, multiply everything by 2 and you get -2 is equal to sine of 4t. So when is the sine function equal to -2? Never happens. So that was a case of the person writing this problem being a stupid idiot. But anyways, that's the approach you would take in a problem like that. What? Oh, there is. Oh, I didn't copy that. Yeah, that's right. And so what's the object's position? Well, it never changes direction, so that one doesn't work either. So, well, yeah, so this function looks like this. If you plot this velocity versus time function, it looks like this, and so we're trying to answer questions about when it's equal to 0, and it just never is. Okay, so in future years, I need to change that question. If I had happened to make this acceleration function like 4 cosine 4t, then we could have found it. Or if I would have changed the boundary condition to something else, we could have found it. Let's do that. So how about this? So let's say that the velocity is equal to 0 when time is equal to 0. So on your homework, you can just say that problem doesn't work. But let me show you how this would work if it did. So we would have still gotten this when we did the integration. And then our boundary condition would have said when time is equal to 0, velocity is equal to 0. So 0 is equal to 1/2 sine of 4t plus c. So c is equal to 0. And so the velocity function is 1/2 sine of 4t. And now we want to find a time value where this is equal to 0, because that's where it changes directions. So find time where the velocity is equal to 0. And 0 is equal to 1/2 times the sine of 4t. So sine of 4t is equal to 0. And at what times is sine of 4t equal to 0? Pi, yeah, right. So it's so it would be like n times pi over 4 for n equals 0, 1, 2. And we're looking for the one that's between 0 and 0.75. Well, if we're including 0 in that range, then 0 is one of them. Pi over 4 is less than 0.75, so pi over 4 works. So either of these two are in that range. Yep.
0.78.
Oh, okay. Oh, good. No, you weren't. Okay, so 0 is the answer. And now we want to find the position when time is equal to 0. Any questions about that part? Well, if you plot this function, we're just trying to find the time values where this function crosses the x-axis, where this function is equal to 0. And so sine is equal to 0 at every at 0, pi, 2 pi, 3 pi, 4 pi, right? Cosine is equal to 0 at pi over 2, 3 pi over 2. Okay. So these are all the possibilities, and then we're just taking the one that's in that range that was given. So now for part B, we want to find the position at time equals 0. Given that oh, this is another sort of funny question. Assuming its position is 5 meters at time 0. So given that at time equals 0, position equals 5 meters, well, since it turns out that the instant we're looking for is time equals 0, the position is 5 meters. But what you would have to do normally with that is you'd have to integrate again to find these questions. Most of these questions I have written without doing them, so occasionally this is going to come up, But if the time when it changed directions was something different than 0, what you would have to do for part B is integrate that velocity function and then use the boundary condition to find the position function, and then, plug in the time. Any other questions about that one? Any other homework questions? Okay. So let's say that a ball is launched from 1 meter high at an angle of 50 degrees above the horizontal. And we want it to land in a cup that's a distance of 3 meters away horizontally. And given that the cup is 0.2 meters high. So first, what has to be the initial speed of the ball? Second, how high is the ball at the highest point? And third, what's the ball's velocity just before it hits the cup? Okay, is this one constant acceleration? It's a free fall problem, so any free fall problem is constant acceleration. So let's first make our choices of the coordinate system and what's going to be time equals 0 and what's going to be time final. So for part A, we'll just do it piece by piece. I pretty much always choose the coordinate system to be on the ground or the lowest thing that sort of comes up in the problem beneath where the object is when time is equal to 0. We're going to make time equals 0 be when it's launched. So I'm going to put the coordinate system here. And also in free fall problems, I always put the y-axis up. So okay, our time equals 0 is when it's launched. What's our time final? Yep. You can only calculate things at time initial, at time equals 0 or at time final. So you're making those choices based on where you have information and where you want to find information. And then the coordinate system that we're choosing is shown. So now let's think about what values we know, what values we want. Do we know time final? Nope. Do we know acceleration?
Yeah.
Okay, so acceleration x is 0, acceleration y is negative 9.81. Do we know the position when time is equal to 0?
Yeah.
That's just the coordinates of the ball here. So it's going to be 0x, positive 1y. Do we know anything about the position at time final?
Yeah. 3 and then 0.2.
Yep. So there we're looking for the coordinates of the point there. So in this coordinate system, that's positive 3 in the x direction, positive 0.2 in the y direction. Any questions about this yet? Okay, so now we're getting to the velocities. Do we know anything about the velocity at the start?
No.
We don't know the speed, but we do know the direction. So for doing the velocity, we know that it's a vector like this, and we'll say that the magnitude is v. We don't know what that is yet. But we know this angle is, did I say 50 degrees? And so we can represent everything in terms of this one variable v. So this vector v sub 0 is equal to v times the cosine of 50, v times the sine of 50. Which is 0.643 v, 0.766 v. And so we can represent these v0x is equal to 0.643 times capital V, and v0y is equal to 0.766 v. And then do we know anything about v final? No, we don't know anything about that. And so we're trying to calculate this this speed v. So is there any equation where this v is going to appear and where everything else that appears shows up in this known list? I don't think so. So in that case, we have to find an intermediate variable. And the one you're almost always going to use is time. Okay, so is there an equation that has time final in it and everything else in it appears over here?
PF.
Yeah, PF, and I think the one that we need to use is the Y. So PFY is equal to P0Y plus V0YTF plus 1/2 AYTF squared. So PFY is equal to 0.2. 0.2 is equal to 1 plus 0.766 times V times TF minus 4.905 TF squared. So 0 is equal to 0.8 plus 0.766 V times TF minus 4.905 TF squared. We need to come up with an expression for TF. How are we going to do that? Quadratic formula, yep. So TF is equal to negative 0.766 V plus or minus, what's 0.766 squared? Okay, so 0.586 V squared minus 4 times 4.905 times 0.8. So that is 0.8 times 19.62. What's that? .8 times 19.62. 18.696. 15.696. That's all square root. And then divided by 9.81. Square root of 15.696. Just to get a sense of the. Okay, and this term is going to be positive. So if we want to have this is a negative 9.81. We need to have a positive time. So the only one of these that is going to turn out positive is 0.766 V over 9.81 plus 0.586 V squared plus 15.696 square root over 9.81. Okay, that's pretty ugly. But now we have TF. That becomes one of the things we know. And now we can look for an equation that has V in it that we can look for one that uses TF. We couldn't before. So what equation can we use now? I think probably the X version of the one we just used. So PFX is equal to P0X plus V0X TF plus 1/2 AX TF squared. AX is equal to 0, so that goes away. And we have that 3 is equal to 0 plus 0.766 V over 9.81 times V0X was 0.643 V. And then plus this ugly thing. Over 9.81 times, again, 0.643 V. Holy moly. Okay, so are we going to really go through all this? So, well, dang it. Okay, let's do this instead. I'm going to give you one that I know the solution is going to look better for, that's going to follow sort of similar process, and you can work through it on the board, okay?
No.
Okay, so this one, this basketball player, he just shot this ball. Okay, that's what you look like after you shoot a basketball. And you say like, nothing but net, and you just stand there.
Waiting.
It's pretty good form.
The horizontal distance from the free throw line to the basket is 4.572 meters. Anybody know how high the basket is? 10 feet. And in meters, that is 3.048 meters. Yeah, that's true. And let's say that we know that the ball is released at an angle of 45 degrees, and it's released from a height of 1.5 meters. So I guess it's just not drawn super to scale. So first, how fast is the ball shot? What's its speed when it's released? And second, how high is it at the highest point? Okay, is this going to give us the same? Well, let's try it. Is this going to come up just like the problem? So the answer for the speed is 8.23, and for the height was, what was that one? 3.22. I don't know how far you can get in this one, but let's do one more. So we did that one last class where showed why if you fire a bullet horizontally, it hits the ground at the same time as a bullet that you just dropped. So let's see what happens. When they did the experiment, it was basically right on, but they were off by a few milliseconds. So let's do one and just see how sensitive that is to how horizontal the gun is. Okay, so let's say a bullet is fired at 1,000 meters per second. From a height of 1 meter. What's the difference in the time required to hit the ground between when the bullet is dropped and second, fired 1 degree above horizontal? So 1 degree isn't very much. It's hard to even see that with your eye, but this is going to give a considerable difference in the amount of time it takes to hit the ground. Like a surprising amount of difference. Okay, any questions about that? Questions? Okay, do it.